So let me start, because this is a different kind of talk. I mean, I will try to give you an overview of what we do at CERN openlab. Without really going into the details, I'll be happy to answer your questions, because there's no way I can actually spend these 20 minutes focusing on specific topics. Let me first start by telling you what openlab is. Even people at CERN sometimes don't really know what we do, where we are. We are a section in the IT department. And we focus on building collaborations between our community and external communities and companies in particular. So this connects very much to the discussion that was done before during the panel on multidisciplinary and collaboration across communities. CERN openlab exists since quite a few years. We are going to celebrate our 28th anniversary next year. I mentioned focus on collaborations. We can describe it into a few major points. The idea would be, this is actually what started openlab, is really trying to understand how we can use any new technology that is available outside of our domain in order to improve research within CERN. And so this is done through joint collaborations and R&D projects with ICT, but also other institutes, other labs, and other fields. So there is a lot of innovation and knowledge sharing activities. There is also a lot of communication and education. You might know about the CERN Summer Student Program, and openlab drives a second program that is very, very successful. So I mentioned joint R&D project with ICT. This is a long, a very messy slide describing what we do with different partners. So what I really want to talk to you about today is examples of what we do concerning machine learning and deep learning. As Maurizio mentioned before, it's been years that different actors are trying to pull or to bring these kind of technologies within our communities, which is very, very conservative. I think the idea of linking and looking out and reaching out and working together with other communities, it's really helping in this direction. So I also would like to point out, actually, when we say, because openlab is a very small section, so not everything you'll see or I will talk about actually happens in openlab. So I want to stress the fact that many of the projects that I mentioned are actually, openlab sets them up as a foster, as an, how should I say, a section that is trying to help collaboration and setting up frameworks for then other groups to actually collaborate with this or that industrial partner. Okay, unfortunately I missed this morning sessions. I don't know how many times you've already discussed the challenges related to high luminosity LHC. For those of you who joined this afternoon, like me, I will just quickly remind you that I think the latest schedule now sets beginning of the high luminosity run at the LHC sometimes in 2027. There's a huge challenges as far as computing is concerned, which will be the community will face. And this is because the luminosity of the accelerator will increase by a factor 10 at least. There will be much more data that will be collected by the experiments, and these data will be much more complex. So connected to this, the data and computing challenges that we have to face can be, are shaped across different, let's say, possible problems and possible approaches. So I would say when we talk about computing challenges, we cannot avoid discussing the problem of resources, which are, if not, let's say, greatly increasing, at least, if not flat, they are slowly increasing or less than what we actually would like them to. So, but this also is a reason for us to become smarter, and so to work very much in trying to increase performances of our approach, and sometimes also start to looking into entirely different approaches. And so, deep learning is certainly one of those fields. Taking this in mind, CERN openlab is focusing on three main areas of research. It's more of a detail, let's say, but we work with 3 years phases. So today, 2020 is the last year of our 6th phase, which focused on those 3 main R&D areas, namely data center and performance, scale-out capacity, including introducing the use of HPC and cloud resources into our computing model, and change of computing paradigms, and in particular research in everything that's connected to machine learning and deep learning. So, what do I mean when I say research on machine learning and deep learning for our community? There are a few points that I believe were touched by many examples in the talks that you saw so far. So we are interested both in everything that concerns models themselves, so development of applications for solving specific problems, so development of new, mostly actually it's not so much development of new model. We are more into optimization of whatever seems to work very well, or other communities are very happy about, into our own problems. That is the technological challenge part, which concerns everything that is related to improving the way, for example, we train our model, speeding up the way we do inference, and those are actually very, very important points, in the sense that depending on how fast you can run your training or your inference, for example, there are many different applications that can open up to the use of the model you're developing. So those are not just, issues about saving resources. Of course, deployment is also very important. Development, there is a lot, most of the work is usually devoted to prototyping. That is the fun part, right? When you are there and you're trying to develop the new model and improve its capacities in order to solve the latest problem. Then there is the phase in which those models have to be interfaces integrated in the way we do our research. So those have to be integrated in our computer models. They have to be efficiently deployed, and they in such a way that we can use them and it can make life easier for the computer scientists, not the data scientists. There is another part, which is, again, strictly connected to what I mentioned before about bridging out to our communities. We are collaborating very much with other fields, in particular on Earth observations and medical fields. We believe, as was said before, that as physicists we can help advancing other sciences as well. So we try to do that. And since a couple of years, we started looking into quantum machine learning. So if I have time, I will also mention something about that, since it was a question that was raised before. So very briefly, I will give you an example of what I mean when I say we develop models. This is an example of a generative model that was developed a couple of years ago to reproduce detector outputs, so simulation of particles, single particles. In this case, you see images of electrons traversing a detector, depositing their energy in those specific detectors, calorimeters for the physicists who are here. This is nothing. It was a GAN model. We did spend a lot of time. This was a project that was developed in collaboration with Intel, for example. They were very, very much interested in both the, how should I say, these all things started a couple of years ago, and they were very much interested into understanding if and how x86 architectures could be used to train these models. On our side, there was a lot of work in trying to understand physics performance. So we are not just creating nice benchmarks. We really want to make sure that those kind of things are usable. So we spent, again, quite some time working on validation of the results. But we were also, is this a pointer, right? Yes. So we also, and the results you see here were obtained in a tight collaboration with Intel, and Sarah from the Netherlands worked on understanding how we could speed up training. And you see an example on scaling training of this model across 256 nodes of one of the latest Intel Xeon processor, the Cascade Lake, it's codenamed. I believe the real name is second generation Xeon scalable processors. That's how Intel calls them. It's a word that, well, the approach that's used here is data parallel approach, nothing really fancy, but it was really nice to see that we could bring down training time of this model in just a couple of hours. There is another thing that's interesting for the physicists that are here. Maybe this is obvious for people that are not working on simulation so much, but when you get used to running Monte Carlo models, which are very precise and are state of the art, and I just, I want to stress it once more, but when you see that you can generate the same detector output in just one tiny fraction of time, here the speed up is a factor 20,000, then you start thinking about different ways you can actually use these tools. I mean, one of the problems we have today, it's even where do we store our data? If we manage to generate it so much, we might, in such a fast way, we might get to the point in which we don't care about storing it anymore. We just simulate it on the fly, just saying. That's an example of what I mean when I say test and optimize models on different resources. We also look into specific hardware. So Maurizio again mentioned before how interested we are, the community is in particular in trying to optimize and run deep learning models in real time in order to improve the way we select data and we store the data that is, the best possible data for our research. That is one of the cases in which, for example, having a very fast inference running on specific hardware or FPGAs would be very, very important. So this is also something else that we do. What I would like to stress is the fact that in most cases, the models that we use are not just out of the box. They are highly customized and therefore require also quite some work in as far as deployment is concerned. So I mentioned FPGAs, or in general, heterogeneous computing. Again, for CERN, for high energy physics community, this is actually a very big issue in the sense that you might have heard about the LHC computing grid, this huge distributed computing system, which is spread across hundreds of sites. It totals up to 800,000 cores, and those are all or almost all x86 machines. All right, I really have to speed it up. So for us, starting to look into diversifying hardware is actually a very, very big issue. And you can see here an example of the research that are ongoing for running, in this case, is an example of a convolutional neural network for neutrino identification in the Dune experiment deployed on FPGA. Another example, this is as far as HPC and cloud are concerned. When we talk about deployment on HPC, we are talking about something that is not trivial in the sense that the two communities are coming closer together now, but they come from very different worlds. And in particular, when we talk about AI, or what people that work in AI would like to see in an HPC center is really like having access to computer-intensive hardware, having all their best or optimized framework available, and having a way of having, of course, workload framework, workload management frameworks available in order to simplify as much as possible. Deployment as much as possible. And so we have we work also in these directions, both on HPC and on cloud, commercial cloud providers in particular. And this connects to what I said before about the fact that most of our models are highly customized in most cases. What's being used by outside communities as machine learning as a service is not something we can just use out of the box. This was a nice example that was presented at KubeCon. It was presented a few times, and it was a nice stunt as the authors themselves decided to define it. So they managed to reproduce using Kubernetes on Google Cloud the whole of the Higgs analysis in just a few minutes. So I will let you have a look at the video presentation. The video with their presentation is really, really nice. If you look at it, you will see the Higgs signal rising up in just a few minutes while running on Google Cloud. They used around 20,000 cores for just 90 seconds processing time. Just very briefly, because I think I'm out of time, I will just mention, I wanted to give you an example, since we're talking about collaboration, cross-communities collaborations, and multidisciplinarity. I wanted to give you an example of what we do with the UNOSAT and UNITAR, the United Nations Institute for Training and Research. So we helped them develop a model to do shelter recognition in refugee camps. This was actually a very small project that a student of ours did in just a couple of months. Retraining a framework, a region-based convolution and model from Facebook AI in order to, what does the GAN thing? I'm sorry about this, didn't realize I have a nice physics plot on top of the shelters. This is internal correlation between synthetic generated data, by the way, if you want to know. And so this became part of a larger effort. Okay, yeah. A part of a larger effort between UNITAR and Global Pulse in New York City. Their headquarters are in New York, but of course they are part of the UN towards the development of AI-assisted toolkit in order to do mapping of critical areas and speed up disaster relief. You can see here an example of a screenshot of a toolkit that's being presented just in a couple of weeks at the AAAI 20 in New York. Quantum computing. Someone asked about quantum computing before. It is clear it's one of the biggest, hot topics today. There are, if you just look at the quantities of initiatives that are going on around the world, and Europe is not bad, and CERN is getting involved. The community is started to be very, very active, and we I started a few projects on quantum machine learning. On quantum computing in general, I'm mentioning here a few examples of recent research we did on machine learning models implemented as quantum circuits. So all of those examples are done in collaboration with companies such as IBM or Cambridge Quantum Computing or Intel itself and different institutes. So you can see some nice examples here of classifiers, quantum versions of classifiers run to reconstruct Higgs to reproduce Higgs analysis or SUSY analysis. Even we have a small example of quantum GAN for fast simulation and graph neural networks. And I'll conclude. We just recently had, last week, we had the OpenLab technical workshop, which reproduced most of the work, which presented most of the work I presented to you today. So if you want to have a look at what we actually do and more in details, you could go and have a look at this link. I think in general, CERN openlab is a very exciting and as a very exciting and diversified research program on many different things, but in particular on deep learning. And I think it's important to stress, and probably all of you agree here, that deep learning in particular is a field that evolves very rapidly, and therefore interaction and collaboration between the different communities is really key. And it is probably not necessary to stress that here, but in more when I give this talk to our community, I really try to stress a lot the fact that industry is playing a big role in this, and so we should never forget to tight collaborations with them. Thank you. I believe I'm in.
Thank you very much. So, thanks for sharing these exciting activities of OpenLab. Are there any questions from the audience? Yes, Shirley.
For the quantum GAN or quantum SVM, what is actually are these actually run on that cannot be run on quantum computers? Is it just like quantum-like algorithm?
No.
If quantum computer was working?
So this one. So those works are done using IBM simulator, quantum simulator. But the quantum SVM for Higgs boson analysis has actually been run on real hardware too. So I reported this here. So one of these curves that you see, those are just the RAC curve for the classifier. So you have a classical BDT, you have the quantum GAN on a simulator, and you have an SVM, and you have the quantum SVM run on a hardware. So these are the 20. This is the small, the 20 qubits IBM hardware that's available today. So it's nothing very big, but it's already there. Now you see some degradation on performances. I'm talking about the yellow curve. But if you think, I mean, this is real quantum circuit run on quantum hardware. I mean, it's, when noise will be better understood or under control. I'm sorry, what? Yeah, the network is implemented as a quantum circuit, so you run both the training and the inference on it.
Other questions? So you mentioned OpenLab just celebrated the 20th anniversary. Do you see any...
Next year.
Next year, okay. Do you see any transformation for, you know, for the next 10 years, let's say, you think?
Again, let's say next 3 years. So
3 years.
as I mentioned, we worked in phases. So next year we will start our phase number 7. So we will spend basically all of this year trying to collect from the community also use cases of what are the directions that they feel are more interesting. I don't think we will move away very much from what we do today. So the areas, in particular the areas of HPC and deep learning will be very relevant. I'm sure we wouldn't want to drop also other things that we do concerning, for example, test of new hardware for storage or, you know, very specific data center kind of technologies. But I would say HPC and deep learning will be the two main things. So we'll come up with the precise plan by the end of the year, actually.
Okay. All right. Thanks a lot. Let's thank Sofia again.